All right, so it turns out that very often the data that you've actually collected and the data you have available to you in your data set may not be actually the best data to be making your predictions or to be making your model with. And so, one of the key things that you can actually bring to a business or an internship is the skill and creativity to actually make your own new variables on the fly, which actually might help to predict Y better than the data you just have currently on hand. So, for example, just to motivate this, let's imagine that we wanted to predict the weight of some tree, and we've measured the relevant variables. We've measured the height of the tree, the density of the tree, and the circumference of the tree, how far around that tree actually is. So in our data set, we would have essentially four columns, one with weight, and then three with height, density, and circumference. And if we just proceeded blindly, the model that we would fit would be predicting weight from just a weighted sum of height, circumference, and density. And that's how regression normally proceeds. We have our columns that have each variable, and we just fit a multiple regression model with them and just see what the results are. However, in this case, that's not a very good model because the real world really works differently than this. The weight of an object isn't just a sum of these three values. In fact, from physics, there's actually a formula that relates the weight of an object to the volume times the density of the object. Normally, that weight is equal to volume times density. So, in fact, we can be a little bit clever about this situation and define a new variable. I'm just going to call it x. And let's define it to be the product of the three predictor variables that we've measured, height times circumference times density. Well, if a tree was a perfect cylinder, the height times the circumference would actually give us the volume of the tree, and then the volume times the density gives us the weight of the tree, assuming the density was constant. So it would make much more sense actually to just fit a simple linear regression relating weight to x, where x is the product of these three variables. And so very often, creating new variables is going to be the key to a model's success. And the hard part is knowing, well, what variable should I really be creating? And unfortunately, there's no sort of process that's going to guide you to the best new variables you could create. It takes a lot of trial and error, a lot of creativity, a lot of intuition, and sometimes domain knowledge about the problem in order to create intelligent variables. So by domain knowledge, what I mean is that you know enough about the problem that you can construct new variables that seem to make sense. Like me, I know something about physics, and I know that weight is volume times density, so that guided me to create this new x variable of the product of the three. And so let's just see where this is actually panned out. So on Kaggle.com, there is a one-day challenge that asks to predict the sales of a newly launched product half a year after its release based on information about the first fourth of a year after its release, from weeks 1 to 13. So not only that, but we also had the number of stores that were planning on selling that product on week 26. That's something that's planned really far in advance. And so if we just look very briefly at this data set, this is the product launch data set. Here's the information that we have. We want to be predicting the amount of products sold week 26. And I've trimmed down the data set a little bit just on odd numbered weeks. I have the number of stores selling that product and the number of actual sales for the 13 weeks, along with the planned number of stores selling it on week 26. So if I were to look at a scatter plot, say just relating the number of items sold week 26 to the number of items that were sold on week 13, what I see is a scatter plot that is troublesome to me. I see that very obviously I have unequal vertical spread. There's very little scatter on the left and a lot more scatter as we go towards the right. And so first off, that's going to suggest to me that, hey, I actually don't want to predict sold week 26, but I actually want to predict a transformation of that. And typically the standard transformation in business analytics is to predict the logarithm of something. And so let's actually do just that. So let's take that data set and predict the logarithm of the amount of sales on week 26 with every single variable that's available to us. And so if we do that, we actually get what looks like a pretty decent model. R squared adjusted is 62%, and that's pretty high for a model in business analytics. However, just because a model has a relatively large R squared or R squared adjusted doesn't mean that it's fitting the data very well. Indeed, if we run check regression on that model, we see a very tragic looking residuals plot where there's a tremendous amount of curvature, very obvious non-normality in the residuals, and so it's actually a pretty bad model. It fits the data decently, but that assumption behind the regression model isn't holding up, so we can do better. All right, well, the winner of the competition, in fact, the winner took home $5,000 for coming up with this approach, assumed something particular about the way that sales was going to work. He assumed that after the first 13 weeks, customers more or less know if they like that product. And so he assumed that the number of sales per store would stay roughly the same from week 13 to 26. So if we know how many stores are selling that product week 26, let's just multiply that by the number of sales per store. And the best guess is kind of what's going on week 13. So here's the ratio, sales per store in week 13, and then just multiply that by the number of stores selling that in week 26. That should give you a pretty good idea of the number of sales in week 26. And he took it one step further. He actually didn't model that quantity specifically, but he modeled the logarithm of that quantity. Like I've mentioned before, the log-log transform is very often employed in business analytics, and it succeeds pretty well and exceeded pretty well here. So in fact, what he did is he took with what was originally a very large data set, basically I think 13 or 14 predictors in here, and converted it into a simple linear regression using only one predictor, Z, which was the logarithm of the ratio of the sales per store in week 13 times the number of stores planning on selling that product in week 26. So here just our syntax here, I'm defining the new variable Z and then fitting my simple linear regression, predicting the logarithm of the sold week 26 from Z. And I have a tremendously successful model here, an R squared adjusted of about 98%, which is almost unheard of in business analytics. That's huge. And the residuals plots don't look all that bad. We fail all the tests of assumptions, but we have a huge sample size, so we need to look to see, okay, well, are the violations obvious and severe? Looking at the residuals plot, I don't see any sort of curvature, so I'm not worried about nonlinearity. And I see more or less equal vertical spread, which is nice. I see kind of this weird pattern, this diagonal line going down here and diagonal down here. It turns out those correspond to products that really didn't sell anything in week 26. And so these represent the zeros essentially in the data set. And there's some violation of normality here, not too surprising because the number of sales is an integer amount, just like the number of football wins. And we know integers never follow the normal distribution, and so there's a little bit of an issue with normality, which is anticipated. However, the model fits the data extremely well. We'll get pretty accurate point estimates for what the number of sales are in week 26. We weren't able to make inferences necessarily all that well because the violations are pretty severe here. But it just goes to show you the power of actually creating an intelligent new variable. And in fact, sometimes you can greatly reduce the number of variables in your model by the intelligent creation of one or two, like what we see here. So we'll learn how to add new variables to data frames in R and how to fit those models in our in-class activity after the exam. So I'll stop part 2 here.